Now we're gonna start a new chapter. Chapter 3, Vector Valued Functions. For this lecture, we're gonna discuss only one section, section 3.1. This is the last section for this week, the vector valued functions and space curves. Let's define a vector valued function. A vector valued function is a function of the form r of t. R is a vector in function of a parameter t equal to f of t times I. I is a unit vector pointing in the x direction, and f of t is a real function. R is a vector function. F is a real function. Also for the y component, this is a real function multiplied by j. In 3D, we will add a third component, which is the k unit vector pointing in the z direction, and a real function h. So we can say that the components f, g, and h are real valued functions of the parameter t. The vector functions R is written in linear combination form. We can write it in component form as such, and this is the x component, y component, and z component for the vector function R. In this example, we need to evaluate r of 0, r of pi over 2, and r 2 pi over 3. We will take the parameter t equal to 0, equal to pi over 2, and also to pi over 3. And we need to answer whether these functions have domain restrictions. For part A, r is given equal to 4 cosine ti plus 3 sine tj. Let's start with the first one. Let's calculate r of 0. So for t equal to 0, replace them in the cosine and sine and the vector function, and calculate, you're gonna get for I. As you can see, the R is a vector function, and it is expected that you will get a vector as a result. Now, for the second one, R equal to pi over 2, replace pi over 2 in the x and y components of this vector function. Cosine pi over 2 is 0, and sine pi over 2 is 1. 1 times 3 is 3. 3j. R of 2 pi over 3, replace it also in the x and y components and calculate, you're gonna get this result. Now, is there a domain restriction? No, there's no domain restrictions. The function is valid at all values of t. Now, for the second part, we have this function. Since we have tangent and secant, we expect that there will be a restriction since these functions have restrictions in their domain. For the first one, we're gonna replace 0 in R, and after calculating in the three components, of course, because this is a 3D function, and after you're doing the calculations, you're gonna get 4j, so no problem. For R pi over 2, we know that tangent pi over 2 and secant pi over 2 are both undefined, so there's no result that exists for R pi over 2. So this is a restriction for this vector function. For R of 2 pi over 3, replacing this value in this function, you're gonna get this result. Okay, so this vector function is valid for all parameters t except for pi over 2. So we're gonna write it in this as follows. So the domain of this vector function r of t is equal, we're gonna open the braces, which stands for, we use this designation for sets, for listing all the numbers in the set. So all the numbers for t are valid. They exist as a solution for this vector function. They exist in the domain for any value of t except for uh, multiples of pi over 2. So the tangent and the secant functions are not defined for odd multiples of pi over 2, not only for pi over 2, for any odd multiple like 3 pi over 2, 5 pi over 2, 7 pi over 2, 9, etc. So all these are odd multiples. How to write this one in one equation like this one? So t is not odd multiple of pi over 2 where n is any integer like 0, 1, 2, 3. Let us explain this. Whenever you want to express an even multiple, you write it as 2n times pi over 2. Why 2n? Because 2n converts your numbers to an even number. Let's consider n equal to 0. For n equal to 0, 2 times 0 is 0. For odd multiples, we're going to use 2n plus 1 times pi over 2. We say this is an odd multiple of pi over 2. This is an even number, even multiple of pi over 2. For n equal to 0, replacing n equal to 0 times 2, 0 plus 1 is 1. For n equal to 1, you get 2. For n equal to 1 over here, you will get 3. For n equal to 2, you will get 4. For n equal to 2 over here, you will get 5. So, etc. As you can see, using 2n, this will give you even numbers. When using 2n plus 1, this will result in odd numbers. For all values of n, which is an integer numbers like this 0, 1, 2, 3, 4, 5, 6, etc. So for all values of n, replacing them in here, you're gonna get the odd multiples like pi over 2, 3 pi over 2, 5 pi over 2, etc. So all these numbers are undefined and do not exist in the domain of this vector function. A vector, a vector is considered to be in a standard position if the initial point is located at the origin. We already know this, that a vector is drawn or graphed at the origin called standard position. When graphing a vector function, we need to graph now in the next slide. We're gonna take an example and graph a vector function. Whenever we graph a vector function, we typically graph the vectors in the domain, of course, of the function in standard position. The vector, the initial point of this vector should be placed at the origin. If you have a 2D vector function, as you can see from this vector function, it's gonna trace a curve. This curve is called a plane curve. If you graph a vector function in 3D, the path it traces called a space curve. Both will give you curves, but simply the terms differs. The term for a vector function, for a curve, for a vector function in 2D, it's called a plane curve, and in 3D, it's called a space curve. And it does make sense because plane, it stands for X and Y plane. It's a 2D. For space, it's a 3D dimensional word. Any representation of both plane and space curves using a vector function is called a vector parametrization of the curve. We're gonna see this in more details in the next sections. We're not going to discuss this in 3.1, but we're going to just introduce the terminology because we're dealing with a parameter t over here. In example 3.2, let's graph a vector function. We are given three vector functions, three parts. In part A, we have this one. To draw a vector function, it's a pretty simple way. We're gonna take several values for t. T stands for the angle, and we're gonna start with the first angle, which is equal to 0. Replace 0 in the x and y components of this vector function. Cosine 0 is 1. 1 times 4 is 4i. Sine 0 is 0, so we're left with the 4i only. So if we want to draw this one, we start with the standard position. The initial point of this vector starts at the origin, and since this vector is pointing only in the x direction in the I unit vector, which is pointing in this direction, in the positive x direction, we're gonna draw this vector along the x-axis. Now, this vector points 4 units. This is the length of this vector. So the length is 4 units to the right. 1, 2, 3, and 4. This is our first vector. We're gonna take multiple points to draw the vector functions in all directions. So let's take another example having a value of t equal to pi. Let's try it out. Replace it in the x and y component. Cosine pi is -1 times 4 is -4i, and this is 0. So at the angle of pi, which is going in this direction, in the negative direction of the negative direction of the x-axis, we place again the vector at the initial point, and we count 4 units to the left because the magnitude is 4. So 1, 2, 3, and -4. This is our vector for t equal to pi. You do the same for multiple values. You draw, and you're gonna get an ellipse, a curve going counterclockwise in this direction. Look at this arrow. Okay, we know that we draw these vectors whenever we have angles and rotations. We rotate the vector in a counterclockwise direction. For the part B,